In this section, we're going to begin chapter 3, specifically section number 1, Introduction to Second Order Linear Equations. So before we get started, let's think about where we've been and then talk about where we're going. In chapter 1, we introduced what a differential equation was. We also discussed various ways to solve first order differential equations, specifically how to solve separable, linear, and other first order differential equations that can be solved via substitution methods. Chapter 2, we discuss some applications to those first order derivatives, such as population models and velocity and acceleration models. We also discussed equilibrium solutions, and we ended with a numerical approximation on how to approximate solutions to differential equations that may not be able to be solved by hand via Euler's method. Chapter 3, we're going to focus on second order DEs. And so we're going to discuss number one, what these look like, what solutions look like, different types of DEs. And then finally, we're going to talk about how to solve these DEs in a very quick and efficient way. So first, let's get some terminology under our belt so that we can speak about these things. We say that a second order linear differential equation is of the form. All right, so we have an A of x, y double prime. The fact that there's a double prime means that it's second order. Then we have plus b of x y prime plus c of x y equals f of x. Here again, the linear portion comes from the fact that the y double prime, and y are all linear. None of them are being squared, none of them are square rooted, et cetera, et cetera. So it has nothing to do with the a of x, b of x, c of x, or f of x. Those terms could be quadratic or cubic or some other kind of power in x, but all of the y terms, y and its associated derivatives, are all linear. So we have the homogeneous linear equation associated with that stated differential equation is the differential equation a of x y double prime plus b of x y prime plus c of x y equals 0. So whenever you have equals 0, that means that it's homogeneous. All right, if the function f of x is non-zero, then we call the linear equation non-homogeneous. So in this upper case, we would say that this is non-homogeneous. These are very important definitions that we'll be using throughout this entire chapter. So make sure you feel comfortable identifying homogeneous means that the right-hand side of the DE is equal to 0. Non-homogeneous means that there is a term in X that doesn't have any Y's or Y primes associated to it that is non-zero here. All right, so unless otherwise specified, we are going to assume a of x, b of x, c of x, and f of x are, quote, nice functions. And I'll say that quite often. I'm saying nice is kind of a blanket statement, but what I mean by that is that they're continuous on an open interval. We're assuming that a of x is non-zero. If it is 0, then y double prime is 0, and it's not a second order DE. So we'll assume that it's non-zero. And what that means is we can divide the entire DE through by a of x, and we can isolate y double prime. So you'll see that now y double prime has just a coefficient of 1 in front, and then we've changed b of x and c of x into this lowercase p of x and q of x. In the homogeneous case, of course, the right-hand side is 0, so we have 0 over here. All right, so our first theorem, which is a very important one, is the principle of superposition for homogeneous equations. All right, so we're going to let y1 and y2 be two solutions of the homogeneous linear equation. Here again, emphasis on the word homogeneous. We are assuming that the right-hand side is 0, and we have two solutions, y1 and y2. So if we have this setup, and if C1 and C2 are constants, then the linear combination of those two solutions, C1y1 plus C2y2, is in turn a solution to the differential equation. So in other words, if we find two solutions, we can make a new solution out of it by taking a linear combination. So this is really important, right? That we can build new solutions based on old solutions. What we'd like to do is illustrate this principle of superposition. by working a couple of examples. So for this first example, we want to verify, first of all, that y1 and y2 are indeed solutions of the given DE. And then we want to find a particular solution of the form C1y1 plus C2y2 that satisfies the initial conditions. All right, so let's take a look here. For the first solution, we have y sub 1 equals x. Now, when I look at my DE, I need y prime, and y double prime. So I'm just going to go ahead and note here, the first derivative is 1, and the second derivative is 0. And then I'm going to plug it into the left-hand side. So that is, I want to find x squared y1 double prime minus x y1 prime plus y1. So that would be x squared times 0 minus x times 1 plus x. And sure enough, that becomes 0 minus x plus x, and that equals 0, which is the right-hand side. All right, so we have just verified that y1 is indeed a solution. We're going to do the exact same thing for y2. So y2 is given as x natural log of x. I need to compute the first and second derivatives. Now, because this is the product of two functions, I'm going to use the product rule when I calculate the derivative. So the derivative of x is 1 times natural log of x plus x times the derivative of natural log of x. So what I'm getting is the natural log of x plus 1. And now I would like to calculate the second derivative, which is 1 over x plus 0. All right, so let's do this again. Let's work with the left-hand side and see if we can get it to be 0. So I'm going to find x2, y2 double prime, minus x, y2 prime plus y2. So that is x squared times 1 over x minus x times the natural log of x plus 1 plus x natural log of x. So let's see what we get here. We get x minus x natural log x minus x plus x natural log x. And sure enough, everything cancels pairwise, and this equals 0. All right, so we have done the first part of this problem, which is to verify that both y1 and y2 are solutions. Now, that theorem that discusses the principle of superposition says that if y1 and y2 are solutions, then any linear combination is also a solution. So what we have here is y, which is c1 x1 plus c2 x2. Nope, let's change those y's to x's, or change those x's to y's. C1 y1 plus C2 y2, that would be C1x plus C2x natural log x. Okay, now we also have the initial conditions that y of 1 equals 7 and y prime of 1 equals 2. All right, now I'm going to leave it as a exercise for you to do to double check that, in fact, C1y1 plus C2y2 is a solution of the DE. So here again, you're just going to use this definition, find its first and second derivatives, and plug it back into the equation. All right, so I'll let you check that. But now what I'd like to do is use those initial conditions to solve for C1 and C2. So first, let's find y of 1. So that would be C1 times 1 plus C2 times 1 times the natural log of 1. Now we know that the natural log of 1 is 0, so that term drops out. And y of 1 was said to be 7. So in conclusion, we see that C1 equals 7. All right, so now I'm going to go ahead and compute the first derivative, keeping in mind that this C1 is now 7. So when I take the first derivative, C1x becomes C1, which is just 7. I don't know what C2 is, but I need to use the product rule. So this becomes C2 natural log of x plus C2x times 1 over x. So this is 7 plus C2 natural log of x plus C2. And now let's use that last initial condition, says that y prime of 1 equals 2, but that is 7 plus 0 because the natural log of 1 is 0 plus C2. And so I conclude that C2 equals -5. And so my final answer here is y of x equals 7x minus 5x natural log of x. All right. So again, just using that principle of superposition to take the linear combination of the solutions to find a new solution, and then using the initial conditions on y to solve for the constant C1 and C2. Now, there's an important remark here that's almost more of a warning, says that theorem 1, that principle of superposition, only works for linear homogeneous differential equations. And this is for second order. And so the next example really wants to call your attention to the fact that this is not going to work if these functions are not linear. So let's look at this next example. It says, show that y equals x cubed is a solution of the DE y double prime equals 6x to the fourth. But if c squared isn't equal to 1, then y equals cx cubed is not a solution. All right, so let's talk about a couple of things here first. The fact that y and y double prime are being multiplied together is what tells us that this is not linear. If it were linear, we would have y by itself and y double prime by itself, but the fact that they're being multiplied makes it not linear. All right, and then furthermore, if it were linear and we knew that x cubed was a solution, then cx cubed should also be a solution. It's kind of like a silly linear combination of itself, right? We're just taking a scalar multiple of it. So this example is here to show you that you must check that you're working with a linear second order differential equation before you assume that theorem is going to hold. So first, let's show that y equals x cubed is a solution. So when I look at this differential equation, it involves y and y double prime. Technically, it doesn't include y prime, the first derivative, but I have to compute y prime just to get to the second derivative. So I'll compute the first derivative, and then of course the second derivative is going to be 6x. So let's plug it in. We have y double prime is x cubed times 6x, which is a 6x to the fourth. And so I'm going to do a check mark because that does in fact match the right-hand side. So now let's see what happens if we try to plug in y equals cx cubed. So number 2, y equals cx cubed. So let's try to plug it in. Let's find the first derivative. That is a 3c x squared. And then find the second derivative, which is a 6cx. And now if we plug it in, y double prime, that is a cx cubed times a 6cx. And that gives me 6c squared x to the fourth. And so the only way that this expression is going to equal the right-hand side is if c squared is equal to 1. All right, so we have just proven that we need c squared equal to 1 in order for this to be a solution. So therefore, if c squared is not equal to 1, then y equals cx cubed is not a solution. So just pay careful attention here that if you're going to take the linear combination of two solutions, you had better be working with a linear second order differential equation. All right, so remember way back when in chapter 1 when we discussed the theorem that involved the existence and uniqueness of solutions of DEs, We're going to revisit that specifically for second order linear DEs. So theorem 3.1.2 says, suppose that the functions p, q, and f are continuous on the open interval I containing the point A. Then given any two numbers b0 and b1, the equation y double prime plus p of x y prime plus q of x y equals f of x has a unique solution on the entire interval I that satisfies the initial conditions y of a equals b0 and y prime of a equals b1. All right, so what this is saying is if we're working with a linear second order differential equation, there is a unique solution for every one of those DEs. So once again, this gives us motivation to study these types of DEs. We know there's going to be a solution. We know it's going to be unique. So we should move forward with trying to come up with a plan of how to solve these types of DEs. And I have a remark here. Theorem 2 implies that two linearly independent solutions, y1 and y2, for the homogeneous equation always exist, but finding them maybe work. So we just learned about this principle of superposition, and we said, hey, look, we can always take the linear combination of these two, but we have not yet discussed how to find those solutions. We've just worked on verifying that a particular function is in fact a solution. So where we're headed in this chapter is how to find these solutions y1 and y2 so that we can find a general solution. But before we get there, we have two more important definitions, namely linear independent and linear dependent. Now, if you've taken a course in linear algebra, these should be familiar terms. We're borrowing these terms from linear algebra, and then we'll talk about why they're important in differential equations. So definition, two functions defined on an open interval I are said to be linearly independent on I, provided that neither is a constant multiple of the other. Two functions are said to be linearly dependent on an open interval, provided that they are not linearly independent. All right, so it comes down to whether they are constant multiples of each other. That's what we want to check. All right, so let's look at a couple of quick examples. Determine whether the pairs of functions are linearly independent or linearly dependent on the real line. All right, so here again, if we're saying that they're linearly independent, they are not constant multiples of one another. So what would it mean for a function to be a constant multiple of another? So I'm going to say that f is a constant multiple of g if f equals cg, right? For c, some constant. And that c could go on either side. You could say g equals cf, right? So what this means is if I divide both sides by one of the functions, then another way to say it is that their ratio is equal to a constant. Okay, so really all I need to do is look at the ratio of these functions and see if I get a constant back out. So let's take a look at number 20. What would f of x over g of x look like? So that would be pi over cosine squared x plus sine squared x. But remember, the Pythagorean identity says that cosine squared plus sine squared is 1. And so these functions have a ratio of pi, right? This is a constant. And so this means that they are constant multiples of one another, which means they are linearly dependent. I will shorten that to LD for linearly dependent. Let's take a look at 22. Let's find the ratio of f and g. And here again, you can either do f divided by g or g divided by f. All we care is that their ratio is a constant. So if you do it one way, you'd get one constant. If you do it the other, you'd get a reciprocal, but the reciprocal of a constant is still a constant. So the order in which you find this ratio doesn't matter. All right, so we have 1 plus x over 1 plus the absolute value of x. All right, now this absolute value of x, remember, is technically a piecewise function. So let's write this over in the margin. We have that the absolute value of x is x if x is greater than or equal to 0, and it's negative x if x is less than 0. So in other words, if your value of your x is positive, or I should say non-negative, then the absolute value sign doesn't do anything. But if it was negative to begin with, it negates it to make it positive. So using this piecewise definition, we can say that this is either 1 plus x over 1 plus x, which is 1, if x is greater than or equal to 0, and it's 1 plus x over 1 minus x if x is less than 0. All right, so it's a constant for all non-negative numbers, but it is not a constant function for negative numbers. The key here is that they asked if they were linearly independent or dependent on the real line. So we're talking from negative infinity to positive infinity. And so our answer here is no, these are not constant multiples of one another, because when x is negative, we have a non-constant function. And so we're going to say that these are linearly independent on the real line. All right, now another way to check for linear independence is by using what's known as the Wronskian. So what is the Wronskian? Given two functions f and g, the Wronskian of f and g is the determinant of the matrix here that is formed by f and g across the first row and their associated first derivatives across the second row. All right, and then of course we know that to compute the determinant of a 2 by 2, we take the diagonal fg prime and then we subtract off the opposite diagonal f prime g. So the Wronskian has a couple of different ways to notate it. We have W of F and G if you want to emphasize F and G, or you can just emphasize the independent variable W of X. All right, so what does the Wronskian have to do with linear independence? That's what we would like to discuss next. So let's take a look here at this next theorem on page 4. It says, suppose that y1 and y2 are two solutions of the homogeneous second order linear equation that's given there on an open interval I on which p and q are continuous. If y1 and y2 are linearly dependent, then the Wronskian of y1 and y2 is equivalently equal to 0 at all points on the interval. If y1 and y2 are linearly independent, then the Wronskian is not non-zero at each point. All right, so the Wronskian gives us a way to compute whether these functions are linearly independent or not. Now, in the case of working with two functions, it's not hard to take their ratio and check if it's a constant. But we'll see here coming up that once we have more than two functions, it's going to be really difficult to check for linear dependence, and the Wronskian is going to be very helpful. All right, so let's take a look at our next solution. Theorem 4 says general solutions of homogeneous equations. Let y1 and y2 be two linearly independent solutions of the homogeneous equations with p and q continuous on the interval. I want to stop and just emphasize that these must be linearly independent solutions. If capital Y is any solution whatsoever, any solution in the world, then there exist numbers C1 and C2 such that this random solution capital Y can be expressed as the linear combination of little y1 and little y2. Thus, the linear combination y equals cy1 plus cy2 is a general solution of the given differential equation. All right, this is another big theorem. This says that if we can find two linearly independent solutions, then that is the key to unlocking every possible solution to a given second order linear differential equation that's homogeneous. So really what this boils down to is finding these equations y1 and y2, because once you have them, every solution in the world can be written as a linear combination of those two. All right, so how are we going to do it? How are we going to find y1 and y2? So in comes the characteristic equation. So let's take a look at what this is. Again, these are terms borrowed by linear algebra. So if you've taken a linear algebra course, these should sound familiar. If you have not taken a linear algebra course, no worries. I am assuming no prior knowledge of linear algebra. The characteristic equation of the homogeneous second order linear differential equation, ay double prime plus by prime plus cy equals 0, is given by ar squared plus br plus c equals 0. All right, so we're taking a DE and we're transforming it to a differential or to a quadratic equation in this case. So one thing that I want to emphasize here is the order on the derivative becomes the order on the variable r. So the second order derivative goes to r squared, the first order derivative goes to r, and this is essentially the 0th order derivative. It isn't a derivative at all. And you'll notice it's an r to the 0. In other words, it's a 1. It doesn't show up. So a lot of times students get confused on how those derivatives correspond to the various r values. So I wanted to point that out. All right, so how can we use the characteristic equation to solve for y1 and y2? So theorem 5 tells us how we're going to handle this if the characteristic equation has distinct real roots. So if the roots r1 and r2 of the characteristic equation are real and distinct, then y of x equals c1 e to the r1x plus c2 e to the r2x is a general solution of the given differential equation. All right, so in other words, those roots just occur as a coefficient inside of the exponential function, and then we're just taking the linear combination of the two. So let's jump into an example here, find the general solution. I have this second order linear differential equation. I'm going to begin by setting up the characteristic equation. So I'm going to denote that by CE for characteristic equation. This translates to r squared plus 2r minus 15 equals 0. So at this point, we want to solve for the roots of the characteristic equation. You can either factor by hand or you can use the quadratic equation, either way. So this is r plus 5, r minus 3. So we get r1 equals negative 5, r2 equals 3. The order in which you name these roots does not matter. So you could let r1 be 3 and r2 be negative 5. And I'm just going to note that these are real and distinct. So this means that theorem 3.1.5 applies, and we can write out our general solution as y of x equals c1 e to the negative 5x plus c2 e to the 3x. Here again, it doesn't matter where you put your c1 and your c2. So if you flip those around, that's just as well. All right, and then at the top of page 5, we have a theorem that tells us how to handle repeated roots. So if the characteristic equation has equal and necessarily real roots, r1 equals r2, then the general solution becomes c1 plus c2x e to the r1 of x, where here again, the root is occurring in the exponential, but because of duplication of that root, we end up with this extra x value here. So let's look at one example to finish off these notes. So find a general solution of the differential equation, number 40. Let's go ahead and write out the characteristic equation. We have 9r squared minus 12r plus 4 equals 0. Here again, you can choose to factor this by hand or use the quadratic equation. This is 3r minus 2 times 3r minus 2. And so in this case, we get r1 equals r2 equals 2/3. So these are repeated real roots. And so we can move forward with theorem 6 that says our general solution is y of x equals c1 plus c2x e to the 2/3 x. And that is our general solution of this differential equation. All right, this concludes the notes over section 3.1. In section 3.2, we're going to do more of the same, but we're just going to generalize it. Instead of second order linear differential equations, we're going to look at nth order differential equations and discuss additional ways of how we can use the characteristic equation to find linearly independent solutions.